this topic actually might be a little bit of out of left field for this group. You know, my colleague Matt Mood is going to speak next week, and he's going to cover a lot of the modeling work that you're used to seeing at previous INSIST meetings on, you know, what we do with simulating thrombectomy on the bench. But when Lorraine asked about topics, I felt maybe this one would be informative for this group, the topic being design of experiment. We have used it in a recent study that Anu Davidi, who you'll be familiar with from the INSIST meetings, carried out looking at thrombolysis. So we'll use that as an example, but first of all, I'm just going to go through the benefits of design of experiment as a approach for bench experimentation. Now, I know a lot of the people online are actually involved in computational modeling and don't work a lot on the bench. But this is an approach, I think, that is widely enough used in the medical device industry, particularly for kind of process development and design improvement and design optimization. But you don't see it, but probably not enough, and I don't see it used a lot in many settings. And certainly before I started working in the medical device industry, I wasn't aware of it. So let's dive in and we'll see. Well, first of all, there's only a small group here. Have any of you used design of experiment approach before?
I have not used it. No.
Okay. Let's see how it goes. Okay. So what I'm going to do is briefly go through what design of experiment is, why we would use this as opposed to sort of our traditional way of doing bench experiments, and explain how you actually use it as well. And you know, I'm not a statistician, and certainly many of the equations behind some of this stuff, you know, I could do it having a better knowledge of. However, it is a pretty straightforward, once you get the gist of it, it's a pretty straightforward way of planning experiments. And you don't necessarily need that in-depth statistical knowledge in order to use it. It is pretty intuitive, okay? And a lot of the material I've taken today are from a book called DOE Simplified by Anderson and Whitcomb. In fact, Pat Whitcomb, I received training from him about 15 years ago on design of experiment. And since then, I've been using it for as many experiments as I feel it's appropriate, because it's definitely in my opinion, a good way to approach problems. So I've put they have a kind of learning tool online as well, and I've left the link in the slides here. And I'll also use Design Expert software today. You can use design of experiment on many software platforms, Minitab, Excel, and so on. But I use this particular one. Okay. So what is it? Okay, so it's sort of an iterative way of doing tests so that you can look for breakthrough changes. So this isn't something like statistical process control or something like this. The aim of why you do design of experiment is to look for the unexpected, or for stuff that will allow you to carry out a process, optimize the design in a way that you wouldn't otherwise have thought of. Okay, so that's really the key here. It's about trying to find a different way of doing things, or an optimized way of doing things. So yeah, it's not, you wouldn't run it on a known process where all you want to do is control the process, you know, trending or looking for outliers. It's all about looking for big changes. Okay, and really when you set about doing a design of experiment, you're looking at casting up a broad net, you know, so you want to explore your full range, push it to as much as possible so you get a directionality from the results that you have, okay? And you're doing this in a very purposeful way, okay? Yes, and another important thing is why you would do this and achieve what we call a design space at the other end is so that you can calculate the risk of making particular changes, okay? And you can model this as well, and I'll show you some examples of that, okay? But first of all, I guess just to this sentence actually, I refer back to it quite a bit, you know, as to what an experiment is. So first of all, it's an observation of repetition in the system at a basic level. You know, it's not, you can't say you have an observation unless you have, you know, shown that you can repeat it. And you need to describe the system that the experiment is exploring. Okay, so what that means is for an observation, you need two or more different results. Use statistics to determine the significance of those results. And, you know, if you have results, you need a measurement system to generate those results, and you need to understand the error associated with the measurement system as well. So an example of this was, you know, the mass of a clot, and this is an example we'll use in this presentation. It's an example of an observation, okay? And repetition, of course, means that the same result can be achieved on different occasions under the same conditions. So if you can't repeat the result, then you don't really understand the system, or your measurement system is crap, okay? And then, of course, you can get a measure of that repeatability using, you know, variance or standard deviation, and so on. And then the system is also another important thing. So this is, you know, describing a set of things working together, your process or your test method, whatever it might be. And that consists of both controllable and uncontrollable factors. And you need to understand what all of those are. And really, this is where your knowledge as a scientist or an engineer comes into play to describe the system. It's that technical knowledge that describes it. So for example, you'll have heard me speak a lot about our models in the past. So our stroke model on the bench is an example of a system, and the factors in that might be the model, pressure, temperature, clot type, etc. Okay. So we'll kind of refer back to these concepts as we go through. So I just wanted to be clear before we went into the rest of it about that. Okay. So step one when we're designing an experiment is define a problem or an objective. So that's kind of experimentation 101. I think everyone who has a lab notebook will write down a name or objective number one. And you know, for us, it could be examples like this. And I'll use this how to make the tastiest popcorn in the microwave as an example in a while. And I'll also use, does RTPA change the mechanical property of a clot in a while as well. So these are the two examples I'll give. So these are example problem statements. So once we know the objective, then you can set about defining the system and the measurement methods. So for example, does RTPA change the mechanical property of a clot? Your system is your blood clot, you know, the hematocrit, the temperature, the time, the concentration of TPA, the pressure that is exerted on the clot are all factors that influence the blood clot. And then, you know, if we're interested in mechanical properties, then some of the measures we might be interested in are fracture toughness or modulus, for example. Okay. Of course, we should also think about, so we know those controllable factors, we have response measures, but we also have to be mindful of uncontrollable factors in the system. So these are things that, you know, might not readily be controlled, such as your temperature, humidity, machine wear, and so on. And they might be a huge source of variation. So you really need to understand other sources of variation and come up with strategies to control that within your experiment as well, okay? And just a little thing, you're all familiar, I'm sure, with a normal distribution curve, the bell-shaped curve. The reason I bring it up and this central limit theorem is just to make the point at the bottom right here. So it's always better to compare averages. And in DOE, when we go into the designs of DOEs, that's what we strive to do. So we're comparing averages. And as a rule, you generally don't want to use fewer than 4 values to generate that average, and the more the better. Okay, so we're all striving for looking at averages, not just individuals. Okay. And then the other thing is, we don't want to presume to know the answers here, and we also want to be prepared to push the boundaries of our system. So we want to get directionality from something that's desirable to something that's undesirable, and we want to establish that direction of the effect. Okay, so be brave when you're kind of putting this together, and make sure you push the boundaries in order to get that direction. The wider your settings are apart, the better it is. However, don't go so far that you're outside all practicality. For example, here, if you're looking at the expansion force of a balloon, you don't want to go up to 1 kilonewton and use that in the brain, because it's going to cause a lot of damage. So just make sure that it's measured. You want to look for wide ranges, but you want to keep it practical as well. Okay. So okay, we can get into why use DOE versus the old-fashioned approach of just looking at one factor at a time. Okay, so why would we do it? So it allows us to measure lots of different factors at the same time, and in a more efficient way than one factor at a time experiments. So what I'm going to point to is these two plots here. So on the left-hand side, OFAT is one factor at a time. So we've two variables, and we've a low setting and a high setting. Okay, so we can take setting A, set it low, set it high, and measure the effect. And same with B. Okay, when in this example we measure B when A is low. Okay, the difference in DOE is, okay, we'll look at A and B, but we'll measure these responses to these settings by varying both simultaneously. Okay, so here, example, we have 4 runs here, looking at low, low, high, low, and we 4 here. So we're averaging across these two numbers here. Okay, and similarly here, we're averaging across here. Okay, but what you miss out on is this point here. So we haven't looked at high, high. Okay, and that might be just where your sweet spot is, or it might have valuable information in your experiment. And what it does as well is it increases the efficiency of your experiment. So for example, you get the same information here from 4 runs than you get from 6 here. And when you multiply that up and look at several factors at the same time, then the benefit increases. Okay, so here we're looking at 3 factors. We get information on all of these settings here that we wouldn't otherwise have got from this way of doing experimentation, just looking at one factor at a time. And this takes 16 runs and this takes 8 runs. Okay, so it's a more efficient way, and it also gives you a better idea of the design space. Okay, so these two, so for these 4 runs on the left-hand side is equivalent to these 4 runs on the lower right here for factor A, and for factor on the low side, and factor A on the high side, these 4 runs here are equivalent to these 4 here. So this is the kind of main concept of design of experiment. You run multiple factors together at high and low settings of each of the factors in a very deliberate way, so that you have a better exploration of your design space in a more efficient manner. Okay, and the more factors you put into this, the more efficient it becomes. Okay, and we generally deal with very complex systems, and the tendency is to break down the system, so we just look at one factor within that system at a time, because we can easily control that. However, with that approach, you may miss out on a lot of useful information, or maybe that setting that's causing you a problem or is an opportunity for improvement. And that's what DOE is all about. It's all about making these kind of breakthrough observations of a process or a system. And that's why it's so useful for improving processes and improving designs. Okay, another few points before we get into some examples. It's very important to randomize, so you have independence of observation, and you're not looking at trends based on how you ran the experiment through a very sort of structured design. So that also helps control against variation that might come from equipment drift, etc. Also, if you do have unavoidable sources of this, then it's better to block those and account for them within the experiment. So if you have to run the experiment over 2 days, and you need 2 people to do it, or in 2 different countries, then account for that within your experimental design. Okay. So when you run an experiment and you get responses for your effects, so this is a 3-factor experiment here. There's 8 different combinations of these 3 factors from low and high, and you get this main effects result, which is looking at the difference between the high and the low of each, and that's the size of your effect. Okay. However, the other additional benefit to design of experiment, which you don't get from one factor at a time, is not only do you see these main effects from the main terms, but you also see interactions between effects. And this is back to what I was saying earlier, where you explore the full design space. So not only do you see the effect of changing A from high to low, B from high to low, C to high to low, you get the added benefit of seeing interactions between these terms with one another and the combined effect of that. So 2-factor interactions here, and because it's a 3-factor experiment, 3-factor interactions over here. Okay, and you can get the size of that effect, and I'll show you an example in a moment. Okay, so the other thing is, once you run your experiment, this is where your stats come in, and what you typically do for a simple experiment is you create a plot like this, a half normal plot, and basically it's telling you which of your responses or terms in your model fall outside what could be assumed to be typical variation or random variation. So anything falling off this straight line is considered a potential model term with a big effect. And then you can select these, include them in your model, and then you can go ahead and do ANOVA and other statistical analysis to determine the size of the effect and whether it's a real effect or not. But this is important because this is how you select terms for your model, and then you can do your predictions and so on, and look at the effect of these terms out the other end. Okay. And then anything that's not included in the model is used to estimate the overall error in the system. I'm not going to get into ANOVA today. Okay, and another major benefit of DOE is, well, what can be seen as a negative is, well, you've so many factors here, right? And you're asking someone to run all these different combinations of your system with different settings, and it can be a lot of work and it can be quite daunting. But what you can do is create fractional designs where instead of running all of the corners of your experiment, you deliberately knock out a few. So here we're knocking out the black corners of our experiment, and that still allows us to predict something. And as your model includes more and more factors, chances are that maybe 1 or 2 of the factors you've included will not be significant, and therefore that adds the overall model error, and then you can get more information from your model than you would have done if you had run a 1 factor at a time experiment. And you can always fold over and increase the design if you decide to do so in the future. Okay, so it's another benefit, and there's several different types of model designs you can choose to use for this. Okay, and just to be careful on that, obviously you can reduce the model, just like this Jenga tower here. So this is all the rungs, for example. You can take some of the Jenga sticks out and still get the same information. You can still see what the shape of this tower is like. You can even take more out and you can still have a general idea, but just be careful not to take out so much, or you won't be able to make sense of the data. And this kind of grid work here shows an example of how you might do that selection of how many factors or how many runs you can leave out and still get valuable information. So what we're looking at here is example of experiments with different numbers of factors, so 2, 3, 4, 5, 6 across the top, and then how many runs if you were to run these sets of conditions here along the left-hand side. So for example, if you have an experiment with 5 factors, if you were to run all of the different combinations, it would be 32 runs. However, you can do a fractional design, get still most of the information and do for 16 runs. So it's an important consideration when you're planning these experiments is to try and reduce it as well to save time and resources. And you can do that in a sensible way by selecting a model that you can afford to run, but still get the information you want. Okay. Another thing to consider is, we're just running 2 points there, right? But it might not be a linear relationship in terms of a response between both of them. So it's important to run a center point in your experiment as well, so that you see if there's any non-linearity between these. Now, this won't allow you to model the shape of that curve, but it'll tell you if it's a non-linear response, and you can always go and explore that later on, okay? If you do want to, if you do assume there's non-linearity, you can always run a response surface model, and here you add additional points. It can be in this shape or this shape, but what that allows you to do is kind of like a, get a graph like a geology map, where your response is the contours of the land, and tells you, it shows you whether you have it allows you to model non-linear relationships. Okay, and that I have an example of that today from a news experimentation where we ran a response surface model for the thrombolysis experiment. Okay, one other point for mixtures. So if you're working on a formulation or a drug product, in these scenarios for a mixture, everything adds up to 100%. If you reduce one component, and the other components have to go up in order to make 100%. So there's a special type of design for that called the mixture DOE. Instead of that cube shape, you can have this triangle shape. So you can see here, as you reduce this factor C here, the other components go up. And then you can combine together. So you can do all sorts of fancy stuff where you combine a mixture and a regular factorial DOE together. Okay. So I'm going to give an example, right? And I'm going to start with a simple example, how to make tasty popcorn in a microwave. And this is an example taken from Pat Whitcomb, which I'm going to share with you. Bring it across here. Can you see this?
I still see the PowerPoint slide.
We see the question.
Can you see? So I need to share my application. Just give me a second. Can you see this now?
Yeah.
Now we see something else. Yeah.
Okay, thanks. Okay. And I'm gonna pop this up. Okay. So this is an example, right? So we have a situation where somebody wants to create the tastiest popcorn, and the factors available to look at are the brand of the popcorn, which they vary, they come with a cheap brand and a costly brand, the power setting in the microwave, and the time in the microwave. Okay, so time is in minutes, power is in percent power, and their outputs in this scenario is the taste test. So does it taste good? And also they want to be efficient, and they want to pop as much of the popcorn as possible. So it's unpopped kernels. Okay, so I'm going to go back to our design expert platform here. So this is that experiment. So we have our 3 factors, and we have the settings of them. And we, in this scenario, already have got the results, okay? So, and I've inputted them here. Here we go. So we have 8 runs. You know, cheap, costly is your brand, time, power, and then your taste is given as a percentage, as a value between 0 and 100, and your unpopped kernels are given as a weight of the kernels left behind after the popcorn has popped. Okay, so this is an example of that half normal plot that I showed you earlier. So it's taking those responses. These responses here on the right-hand side have fallen off the half normal plot. So likely are that they are significant effects. So I'm going to select those for inclusion in the model. Then we move on to the ANOVA, which will give us some statistics around those factors and if we include them in the model. First of all, we want to see is the model itself significant, and we're looking at p-values here. So anything less than 0.05 is a significant term. So the model here is significant, and it's also shown that these 3 factors, your time, your power, and an interaction between both of them are also significant. And then there's a whole bunch of other stats you get to give you a measure on the quality of your fit and the model. Okay, and then there's also a whole bunch of tests you can do to look at outliers and variation and look for normality of your data, which I'm not going to go into today. I'm going to go straight to the models of these 2 responses that we've selected. So we have taste. Okay, so here we have an interaction, right, between time and power. High power in red, low power in black, and time between 4 and 6 minutes. What it's telling us here is, okay, well, at 4 minutes, at whichever power we choose, we get tasty popcorn, and it's less tasty when you have 6 minutes at the high power. Okay, so this simple example is giving us that, and then on the unpopped kernels, we have 2 factors which are shown significant. B being time, so it makes sense. The longer you leave them in the microwave, the more kernels are popped, and higher the power, more kernels are popped. Okay, so that's kind of an example of how you might approach this experiment and how you can, out the other end, and come up with a better picture of your design space, because you've included, you know, 3 factors and you've looked at all of them at the same time by varying that level. And then you do interesting stuff like modeling it and trying to, you know, come up with something that will improve your process. So for example, here we want to maximize the taste of our popcorn, so I've set that to maximize here. We want to minimize the amount of unpopped kernels, and you can predict a space in your experiment which gives you that desired outcome. So here we're looking at desirability. So based on those 2 settings that I put in, that I want the popcorn to be tasty and I want the amount of unpopped kernels to be low, it's predicting a kind of sweet spot up here where you have a short time duration and you have a high power in order to get to that point. Although down here as well, it's almost the same. Okay, so down at this point, so you have a long time and a low power, you're almost getting to the same spot. All right. So you can imagine it's a very simple solution, but when you have a very complex process and it's not as straightforward, and you don't really know what the preferred settings are, this can be very valuable. Okay. And this is just another way of doing the same thing. So here, for example, I've said, okay, I want the taste to be greater than 75. I want the number of unpopped kernels to be between 0 and 1.5. And it gives us a space up here in yellow that we can operate in our process. All right. I'm going to go back to my slide deck. Hopefully you're still with me. So that's really kind of an overview of DOE, the different types of models you can create, why we want to do it as opposed to doing the one factor at a time type of experimentation. And I'm going to finish up with showing you a news example, her experiment looking at the mechanics of clots following RTPA treatment. Okay, so we took the same approach of we had a bit of information from experiments in the lab where we'd taken clots and exposed them to TPA. So we had that kind of general idea of the system and the expected results, but we weren't really sure, right? And we know it's a pretty complex scenario. So we went through this exercise of defining our problem, describing our system. So here I've taken these factors which I described earlier. So the percent of red blood cells, or the hematocrit in the blood mixture used to make the clot, the amount of platelets present, the time, the amount of TPA, and the pressure, or in some way simulating the pressure that can be experienced by the clot in the artery. Okay, and we set 3 measures here: so weight of the clot, the modulus, and the energy dissipation ratio. And with that, we came up with a design. I think it was about 86 runs, and then we reduced the size of that design, as I described earlier, in a sort of deliberate way to bring that down to 39, so kind of halved the overall possible design, with still the ability to look for interactions and get as much information as we could out of the experiment. When we went through this, of course, we started with a list of, I don't know, 20, 30 factors. Some of them we needed to control within the experiment so that they didn't contribute to the sort of random variation or bias in the experiment. And others we included, which I've described. And then the next exercise is to pick settings, okay, that describe your design space. So for percent plasma, which is the opposite of percent red blood cells, we picked between 50 and 100. So 50% plasma meant that 50% of the blood mixture was red blood cells, 100% plasma, and there was no red blood cells in the blood mixture, and any clot that formed was just fibrin and platelets. We looked at the time in TPA, so we varied between 0 and 2 hours, which is, kind of typical. It's longer, right, than the duration of administration of TPA to the patient, but the patient can have, TPA on board for, quite a while after the infusion is stopped. And some patients are treated, really shortly after they've been given TPA in mechanical thrombectomy. So we want to understand, what is the effect of time TPA on the mechanical properties? Contraction force is the mechanical compaction of the clot prior to treatment. The amount of platelets we control by varying the amount of PRP we used, so that's platelet-rich plasma. So at the component of the percent plasma, we vary the amount of platelets within that, so from 0 to 100%. The dose of TPA, clinically, patients are administered 14 micrograms per mil, so we went for 50% lower and 50% higher. And the blood volume was one we included as well, because we felt big clots come in all sizes. And potentially that was something that might affect the measurement. Theoretically, it shouldn't, right? But what we wanted to do was incorporate that in our experiment to account for the fact that it might. So we deliberately included 2 different sizes of blood volume, which resulted in 2 different sizes of clots. So we could determine whether clot size influenced the effectiveness of the TPA, and as a result, the mechanical properties. So that's our system, our problem, our settings. I described this, so this is kind of the workflow of the experiment. So we made up these blood mixtures using different concentrations of red blood cells and platelets and different blood volumes. We allowed the clots to form and contract if they could. Some clots with a lot of platelets contract a lot more than clots that don't have any platelets. And then on top of that, to simulate the action of blood pressure in the artery on the clot, we had a mechanical compaction unit here where we basically squashed clots between a plunger and a fixed cell here, and the serum could drain out, and we varied the load that could be applied there. And then we exposed the clots to thrombolysis, different doses and different time frames. And then after that, we tested the clots using our compression testing, which I've described to this group before. And we also weighed the clots throughout this whole process as well, so we can get a measure of, well, how much did the clots, what are the size of the clots, depending on the different composition, depending on the mechanical loading applied to them. And then after the TPA had time to do its job to reduce the clots by degrading fiber. So these are our outputs. Okay, so mass loss for each individual sample was measured after each treatment. Clots were, in our case, we wanted to be careful not to degrade the clots significantly, because we felt that some of the clots, if they were 80–90% degraded, first of all, there might be not enough sample left to test, plus they might become quite broken up and fragmented, making them difficult to measure, and that will affect the measurement variation. So we deliberately set out to degrade the clots by not more than kind of 25%. So we had enough sample. So we had degradation, but not so much that it affected the sample negatively. Okay, and these are examples of the outputs. So we, the stress strain curve shown here of two different samples, one treated with TPA, one without. And the measures we took off this curve were the slope of the line here, the modulus, at high strain, low strain, and then we looked at the energy dissipation ratio by measuring the area of the hysteresis loop here in the loading and unloading of the clot and their compression test.
Can I ask a question, Ray?
Mm-hmm.
On the slides, the previous slides. So do you mean that you, when clots were degraded more than 25%, would you get them out of the RTPA earlier?
No, that was pre-work, Nikki. So we looked at our experimental runs ahead of time, and we looked at, okay, going into this, we expected that red blood cell rich clots would degrade faster than fibrin rich clots. We weren't quite sure. That's our assumption. We also knew that if we left the clot in there for longer, it would degrade more. So for 2 hours versus a shorter duration. And then the smaller clots would reduce faster, obviously. And we didn't know about dose, but we assumed if a dose was to have an effect, then the largest dose would maybe be fastest. So we ran that condition, and we assessed whether that clot would degrade below 75%. If it did, then we chose a bigger clot size, so that we always so then before we started the experiment, we ensured that the clot that we felt would degrade most would not degrade more than 25% or thereabouts, and meaning that all of the other clots would be kind of there or have less degradation. That's the way we went about it.
Okay. Yeah. Thanks.
Okay. just swap over to the news design expert file now. Let me know if you can see it. Can you see this? Can you see a data sheet with lots of numbers?
We can. Yeah, we can.
And this is kind of the last video, and we can spend a bit of time on this if you like. But this again, similar to the popcorn example, describes our experiments or 6 factors here and the various settings we used. Here I've also the results in, which was this. Okay, so these are all the results based on each and every one of these 39 runs. And then we have various outputs. Okay, so we have the mass of the clot. So that's just in grams. The mass of the clot after it just clotted, that's as a percent. The reason we did that is because when we looked at the mass of the clot on its own, and this is all just fitting the model, so I'll skip through it. Yeah, we'll go to the ANOVA. And what we're seeing here is that every factor actually has had an effect. Let me just do this here again. So they're all in the model here. And so we can look at each of these factors, right? And blood volume is included here as a factor that has an effect, and that makes sense, right? Because we started with more clot. So let me just go back to this. So percent plasma, time in RTPA, contraction force, percent PRP, blood volume, all had an impact. The only one that didn't was the dose of TPA. So what we wanted to see then is, okay, if we take blood volume out and we correct for it, so if we just take the percent size of the clot, accounting for a different starting volume, is that significant? And the answer is no. So if we do the same analysis after removing blood volume, then we're just left with after thrombosis, percent plasma and percent PRP. So accounting for the fact that you're starting with different blood volumes hasn't really impacted how much the clots reduce. Okay, so the only factors that affected that were percent plasma and percent PRP in plasma. And then after the clot was exposed to TPA, I'm going to go back into this here, the only factor that actually comes out significant is the time in TPA. So again, not blood volume, not any of the other factors, which is telling us that really the only, accounting for the fact that the red blood cells, if you have a lot of red blood cells, you end up with a bigger clot. If you have a lot of platelets, you end up with a smaller clot. Aside from the fact that that is going to happen, that does not then, in this experiment, impact the effect of the TPA in terms of reducing the mass, which is a big surprise to us. But what we can say is with kind of confidence that we've included all of those factors in the experiment is that we tend to believe this result. Now, the subsequent work that Anu went on to do, where she put these clots in a vessel model, showed that actually the histology had a huge effect in the rate of degradation, not so much just because the degradation of the fibrin, but more the fact that the clots move more in the vessel under pulsatile flow, and they're also more, so red blood cell rich clots move more, and also they're more likely to fragment and have big chunks break off as opposed to the fibrin rich clots, which don't. So that's it's interesting that what we found was that the size of the clot was only impacted by the time in TPA and not by those other factors in this static model. But we can be confident that that's based on the experimental approach taken. And then the effect of compaction, so compressing the clot. So what's the effect of blood pressure? Here, our model is telling us that we have, percent plasma, contraction force, PRP. We have an interaction term in here, so we can look at that because it makes a nice graph. If I open it up here. So this is, the benefit of doing a response surface model, because, we haven't just run 2 points, we've run intermediate points as well, but we can look at the effect of, it's kind of an obvious effect, but the amount of plasma in the clot ranging from 50 to 100%. When you have more plasma, it means there's fewer red blood cells, and we know red blood cells are not compressible. And the more weight we added to the clots, again, you would think would push out this extra liquid that's in the clot. And that's what we see here. So we see the effect, and we can model the effect of the relationship between the amount of liquid in the clot, it's called its serum, and the weight used to compress the clot. So the higher the weight, the bigger the effect, and that's a bigger effect when you have fewer red blood cells present. And then similarly, we the same for the mechanical outputs. So I'm just going to quickly step through this. So for modulus, the percent plasma, the time TPA, the amount of platelets are all significant terms. But what's interesting is that there's no interaction term. We're a bit surprised by this, so what we're seeing is, or I would have assumed, right, that a clot that is maybe more retracted with platelets, that might change the efficacy of the TPA, and there might be an interaction term there, but that didn't pop out. Similarly, the amount of fibrin or red blood cells in the clot doesn't seem to interact with the time in our TPA. It doesn't come out as a significant term. But that in itself is an interesting result, so when we look at those terms on their own, then, so we can see percent plasma, its effect. So going from 50% to 100% plasma, or 50% red blood cells to 0% red blood cells, this is the effect that it has on the modulus. So it gets higher when you have fewer red blood cells present, which is a result that we've reported before, and it seems to make sense. With time in TPA, what we see is the longer the clots spend in TPA, the modulus decreases, which I guess makes sense as well. I mean, you're breaking the fibers. Now, this is just a compaction test, compression test. So we don't know whether it's more friable or more prone to fragmentation. That would be something good to do in future. And finally, percent PRP. So when you use the amount of platelets present, the clots become stiffer. And this is again a result that Sarah Johnson, in collaboration with Sarah Norris, reported as well a couple of years ago, and I presented to the INSIST group in the past. But what's significant is you don't have an interaction term there, which is interesting. Okay. Do you have any questions on this? Because I know I kind of covered a lot there, right?
I have one, if no one else does. I was wondering, did you you analyze these data linearly? I assume, right?
What do you mean?
So if you looked for this graph that you see here,
Mm-hmm.
that we don't see the scatter plot. Obviously, I was wondering if you looked at that to see if the relationship was more looking linear or not linear.
Yeah, this seems it's linear, so that is done at the beginning here actually. So you do assess whether it's a linear relationship, and you try different fits.
Yes.
And certainly it's a linear effect. If it wasn't, then we would have modeled this that way. Yeah. So
Yeah.
it seems to be linear in this experiment. And that's one of the reasons you'd run a response surface model is if it was non-linear, you had the ability to model it.
Yeah, I was wondering whether it might not be linear, but it's interesting, that it is.
Yeah. Now, just bear in mind, of course, you started out by asking, how much of the plot was degraded. So maybe this becomes nonlinear the further through that degradation process you get. So if it was 50% or 75% degraded. So just within the bounds of our system in this experiment, we can say it's a linear effect.
Yeah, cool.
Okay, doke. So I did that. These are the results. I think Anu presented them before, so I'm not going to dwell on them. And yeah, similarly there, we've kind of gone through these results. And that's it. Thanks, Anu, by the way. And yeah, I don't know if I've convinced you that DOE is a good approach to bench experimentation, but I certainly think it is. And hopefully you see the benefits of it in that thrombolysis experiment we ran. And I'm going to finish at that and answer any questions if you have them.
So maybe you mentioned it, but I have a question on this graph that you showed in the beginning, where you have this ratio of all the experiments you can do, and then you had, I think, green, yellow, and red boxes of how good the quality is when you drop out a certain number of experiments. What is, for instance, the difference in quality if you go from a green to a yellow box, let's say?
Yeah, so the problem arises with aliasing terms. So, for example, generally with the green ones, what you can predict 3-factor interactions and below. So 3-factor, 2-factor, and 1-factor main effects. If you try to do anything above that, there's significant aliasing between the terms. So you need to be careful. But it's very difficult to even I guess get your head around a 4-factor interaction anyway. So generally 3-factor interactions is the limit of what you can process in your head anyway, and it's enough. And once you get into the yellows, then you are given a you really, it's 2-factor interactions, and you can maybe manipulate it a bit to ensure you can look at certain 3-factor interactions that you think are possible ahead of time, so you can augment the design somewhat, but generally you're left with 2-factor interactions, which might be fine, right? Because generally how you would do this is an iterative process. So you might have, start off with, 15 factors in the system, and you don't really know what the effect of any of them are. And in that scenario, you're better off running a much more reduced design. And there's other designs, a lot more kind of screening and optimization designs that you can select that are not represented here. So you'd use that to sort of just identify some main effects. So get that 15 down to, I don't know, 5. And then you run a much bigger experiment on that to really explore that design space. And that's a more efficient way of doing it, because each run you do is costly. So that's a better way to go about it. So you generally start the screening run with lots of factors, get it down to a manageable number. Maybe do a simple 2-level factorial, identify non-linearity and so on. And there you might follow up with a response surface model with fewer terms again.
All right. Okay. Thank you.
Well, if nobody has any other questions, then thanks a lot for being here on this sunny afternoon.
Yeah.